Hello, I'm Namiko Saito from Waseda University, Japan, with JST Moonshot program. I will present a work on real-time motion generation with active perception using attention mechanism for cooking robot. Many daily tasks require us to handle deformable objects like ingredients, clothes, and liquid. Thinking about cooking scrambled egg, the egg is gradually hardened, so the robot needs to steer it considering which part is hard or raw. Handling them is difficult because the robot needs to perceive the characteristics quickly and respond to the change. An act depends on the characteristics which is changing in real time. Cooking a non-scrambled egg requires perception and motion adaptation every moment. In this experiment, we set target skill rules as the size of the egg block is smaller than 15 centimeters and there is no raw nor no burnt part, and aim to make the robots to acquire the skill. The video on the left shows the movement during recording training data in which an experimenter teleoperated observing the egg status. And in the middle is just replay the training motion. And the right is random movement. As can be seen, if the robot simply replay or move randomly, the egg cannot be separated smaller than 15 centimeters and some parts cannot be moved well and burned. We hypothesize that the difficulty occurs because the robot cannot perceive characteristics and generate motion quickly and efficiently enough for handling real-time changes. Each sensory motor includes both important and meaningless information. We introduce an attention mechanism that can weigh the modality in a predictive deep learning model, considering reliability and importance at that time, and realize efficient system. The model is composed of a convolutional autoencoder for image feature extraction and an MTRNN for motion generation. To distinguish between the importance of the modalities at every moment, an attention mechanism is introduced to the MTRNN. The attention mechanism works as a filter to pass data from the input-output nodes to the context nodes. This is the setup. We collect training data with teleoperation, setting some key points and key flipping motions to command the robot. We collected 32 training data with 2 different heating powers and 4 types of ingredients. From this slide, I will show you the result. I will show the video with our proposed model. At first, the robot pours egg mixture with its left hand. This motion is predefined. Then the robot starts stirring and circling inside the pot. From this motion, the robot is controlled with our proposed model. In the beginning, the egg is raw, so the robot steers widely all over the pot. The robot especially focuses on the center of the pot, where the egg is heated and hardened quickly. Then the robot goes to the rim of the pot and steers largely not to make any parts burned. And after for a while, the egg becomes harder and harder, the robot starts flipping motions and turns the egg over. Then the robot cuts and splits the large blocks to make them within 15 cm size. At last, the robot recognizes all the egg is heated and finishes cooking. So the robot could change the way and area to steer depends on the egg status. These motions are not explicitly indicated, but the learning model learned it implicitly and acquired cooking skills from human demonstrations. For evaluation, we tried mixing different ingredients to eggs. We tried with soy sauce and red food coloring, which changed the appearance. We used bamboo shoots and cheese to change touch, and used minced meat and spinach to change both appearance and touch. In all the trial, the robot considered the way to steer and when to finish, and could cook scrambled egg whose blocks are smaller than 15 centimeters and no raw or no burnt part. The robot achieved 90% success rate with training model and 78% with untrained ingredients, which proves high generalization ability. For comparison, we conducted the experiment without attention mechanism, which means all the sensor data is input evenly to the learning module. We tried 5 times, and in 4 trials, the robot pushed out the pot. And in 1 trial, the robot only steered the right side area in the pot, where the arm did not occlude the pot and the egg was visible. Thus, we assume that without the attention mechanism, the robot cannot focus on torque and tactile sensor information and focuses on vision too much. We analyzed the trajectory tracking the tip of the turner. As can be seen, the model without attention mechanism mainly covered the right side of the pot. On the other hand, our model could cover the whole pot. In addition, the trajectories of our model shows that the motions approached the whole area at first, but gradually changed to sharp targeting of specific areas. We performed a survey on the appearance and taste of the scrambled eggs. We took pictures of the dishes cooked by humans and robots with our model, and asked the respondents to distinguish them. As a result, the success rate for the distinction was 56.6%, which is not far from 50%, that is indicating that the robot could cook dishes similar to humans in appearance. We also asked the respondents to grade the dishes cooked by humans, by robots with our proposed model, and by robots without the model in order. Our model scored well in terms of appearance of the eggs, and the ratings were almost the same as those for the humans-made eggs. Next, we analyzed the attention mechanism to confirm the focused modalities each time. We show attention maps, which are heated maps representing the attention weight with whole dimension data, focusing only joint data, and averaging with each modality. The lighter color indicates highly focused modality. When occlusion occurs, we can see vertical wave lines in the heating maps. That represents switch of focus dimension. In the latter, the heat color of joints 2, 4, and 5 became darker and darker, which are mainly used for steering in the foreport. In contrast, joints 3, 6, 7 became lighter and lighter, which are mainly used for steering in the foreport. And torque sensor data increases attention, and whole image decreases attention. We can say that the attention mechanism can focus on important joints and sensor based on the X status and necessary action type. Next, we conducted principal component analysis of sequential CS internal value during evaluation experiments. We showed 2 samples for each heat powers and ingredients. At first, with heating power 190 degrees, the plots flowed from minus to plus along the PC1 axis, and the robot finished cooking. Then, with heating power 180 degrees, also finished cooking. We can say PC1 explained the egg status from raw to hard and provide a complete time of steering. We also tried totally different ingredients. The robot showed movements approaching to and separating the gathering parts. Therefore, we assume that the learning model has a good generalization potential ability to recognize the transition of the status and decides motion and end timing. Finally, we show some failure examples. We use vision, thus dark-colored ingredients were difficult to handle because the model confused with the pot. For example, a large block which contains large spinach leaves is left, and seaweed was difficult sometimes. We also tried spinach and some vegetables and taro potatoes, but they were impossible to handle. Vision-related failure is next challenge to handle. Here is the summary. We realized real-time perception and motion generation for objects whose characteristics change step by step. The approach is introducing attention mechanisms to focus on important sensory information and recognize the characteristics quickly and generate motions efficiently. By experiment, we confirmed that the robot can handle unknown ingredients and the attention mechanism is efficiently working for motion generation. Thank you very much for watching.